Okay, this is my T. It comes here. This will continue till it meets 0, and after that it remains 0. When it has become 0, that decay will not take place. You know, the capacitors charging, that capacitor charging will not take place when it has come to your 0. So it will get clamped here, and your output will be like this. Here onwards it behaves like this. Here your DC has been completely blocked. DC block. So when I say where is the clamping voltage, that means whenever this has touched 0, after that it will remain as such, this. So it is clamped to what voltage? Earlier its DC was somewhere here. Now the DC has got somewhere. I can say VH is clamped to 0 voltage. Your VH is clamped to 0 voltage. And that's how we're going. So if we go by DC, DC will be VH minus VL divided by 2. Sorry, VH plus VL divided by 2. VH plus VL divided by 2. And that will go in the negative direction. VH plus VL divided by 2 is this thing in negative direction. So VH minus this DC, it has come over this point. So that way it has decayed. In the transient response, it is decayed. When I come to the steady state, it has become your DC block, and here the clamping has really taken place till it becomes your 0. Any question, I welcome. I have not put any other, component to complicate the situation for your understanding. So it is just exponentially decaying. Shape is decaying in the transient response. In a steady state, it becomes a clamped, that exactly that square voltage. It will be 0, so here discharge will not take place like that. So it will be 0, then jump here, then it remains at 0 voltage only. Is it okay? Understood it? So when it becomes 0, that you have to compute, that you have to calculate. Only then you can say it is clamped to this voltage. Or if you are very smartly giving the answer, you can find the DC value of the pulse, find from your highest voltage, remove that DC voltage, that highest voltage will come to your 0, this will go to your some negative voltage, and that's how it will be clamped. Maximum voltage is clamped to 0, and minimum here becomes your twice V minus 2V. So it is like that. Now we know this thing. If this is my 0, this is your 2V. V was your VH minus VL. So it is 2V minus 2V. So it is clamped now. Same square wave has been clamped. VH minus 2V or VH minus V, sorry, not 2V. Because I have taken both positive. Yeah. So VH minus V. V was a VH minus VL was a V. So this becomes your, this voltage is becoming VH minus V. VH, that is 0, 0 minus V becomes your VL dash. VH dash becomes 0, VL dash becomes 0 minus V. So that is minus V. Okay. Any question comes to your mind? Yeah, come on.
So what is this VL dash?
What is VL dash? I have written here, I am putting, the pulse initially was coming like this. My datum was here 0. Okay. I call this as my VH and this is my VL coming over there. Is it okay? Become a 0 somewhere here. Now after the steady state has been achieved, it is clamped now. So after clamping, my VL comes here. VH, sorry. VH becomes my 0. So I call this as my VH dash. After clamping, a VHCL I can say after clamping, okay? Then it goes below that. Here it becomes your VL dash or VL after clamping. So that's what you will be getting. The 0, it is going like that. This thing you are getting. There is some tip here. You're going like some kind of your exponential. Here also exponential decay is there. Negative charge will be decaying, and it will be approaching toward 0 from this one. From the negative value, it will be approaching to 0. So there will be some kind of tilt if you calculate by the downwards reverse bias resistance or so. And according to that, there will be one tip here. It will come like that. It may cross 0. It will coming like that. If this is my your discharging through the reverse bias resistance of the diode, this tip will be now decaying with the forward bias resistance of the diode because it has become positive now. That's how it is coming. Is that okay?
Yes, sir.
Fine. Take other example, some other example then. Please feel free to ask because it will be difficult for me to read your, doubts, etc. I cannot see your face. But when we meet in the offline class, yes, I'll be able to read your face and find that yes, there is a doubt in majority of people, and I'll do that. You have to ask questions here until unless things are. Now I'm making another example. What happens? Input is sinusoidal signal. Input is a sinusoidal signal. Okay. Here is my 0. It is coming of amplitude A. It is shifted by something as V reference as a DC plus amplitude, let us say A sine omega t, sine 2 pi fct, whatever is there, omega ct. Okay, this is sine wave. Here is my 0. Is V reference plus sine wave coming over there. Now I'm feeding it to the same circuit. Here is my RS, here is my C, here is my diode. This is going to be the output. This is my RS. Remember, if I put a resistance here, your RF parallel to this resistance will be in one case. Your RR parallel to this resistance will be in other case. So if RF is very low, it will be the RF dominating. If RR is very high, it will be this R dominating. RR will not come into picture. So the lower one we take in the parallel combination that you already know. So I'm not. When I feed to this, what is going to happen? Here it will be. Here is my 0. Okay, so it will be starting like that, and it will be coming down like this. Region I have given there. Okay. I don't think examiner will ask you to calculate these values, but yes, region is coming like that. Is here. Okay. Now it becomes 0. When it becomes 0, it will be like that. or some small tip if you want, you can add it there. According to the numerical question, if the capacitor value is not sufficiently large, etc. is there. So that's how it is coming, and now it is clamped. So what is this voltage to this voltage? Here to here is your 2A. This is your 0, this one would be minus 2A. Okay, so it is clamped. After this transient response is over, it is clamped in steady state. Or you can say the DC has been totally blocked. Why DC? After DC blocking, it is further shifted by the amplitude of that. So not only DC blocking, I think in that case also, I think previous case also I wrote as V only, it will become your 2V. Okay, because the reference voltage will be gone. When take DC value, reference voltage also there. After that, this magnitude also goes down. So it will become 2V there also. So it will be your 2A. Peak to peak will be your 2A, like that. No, that will be only V max or V min, sorry. That of V max is here, V max is your this thing, V min is this thing. Okay, fine, it will be same thing. So that was V means it is okay, fine. So it is your minus 2A. This same magnitude, it will keep on appearing like that. Is it okay? Now I choose a signal. This is my 0. I'm talking of VI here. VIT. I'm taking a square wave which has been clamped. Okay? So that means it is coming like this. It is coming like this. This is a clamped square wave. Okay? This is the one. Sorry, I made a mistake. This is not 0. Let us say this is minus 10 volt. And my 0 is somewhere here. So at minus 10 volt, it is appearing like this. Okay? And after this time, what happens? This all of a sudden reduces its magnitude. Okay? It has come to this point. This is clamped like that. Now it has come to this point here, and its amplitude is reduced from potential divider circuit comes. Some attenuator comes. Then what will happen? It will come up to this point. It becomes half, let us say. It is attenuated by half. Attenuated by half. Attenuated by 1/4 power by 1/4 power. That means amplitude becomes half. So it will go up to this point only. Okay. After that, same thing will happen. Okay. Maybe it goes like that. Here it will be coming. Will it go like that? No. It will be coming like this. It has come like this. Again from here it will be coming like this. Then same half comes here. It is coming like this. Again the same half comes over this point. So it will keep on rising till this peak before coming this point, in between or up to this point, it touches the 0 value. This 10 volt going like that. So your 0 is somewhere here. So till this touches this 0 level, it will keep on going like that. Here I have reduced the magnitude. It was clamped. This is shifted. Now it is given to the same circuit. In the same circuit, it was coming like that. Here also it was not. The moment I put it here, it will be coming it will start going slightly in that direction. You see, Here also it's going in that direction. But all of a sudden I find that after coming to this point, it will come to this point only. This will not be there. This will not be there. After coming to this point, okay, after coming to this point, not here, its amplitude is reduced, becomes half. So half means it go like that. Here, this time this is not there. This time it will go like this. Again, it will be coming over here. It will go like that till it touches 0. So it will keep on growing like that. This is also growing the way it was coming down here. Here also it is growing like that till it touches this 0. After that, it will be clamped to that 0 value. So there is no other resistance, etc., no voltage supply. It will be clamped to the 0. Ultimately in the steady state. This is a transient response. Same thing happened to sinusoidal case also. Sinusoidal case, let us say something has been clamped like that. Oh, okay. Something was clamped like this. Sinusoidal, this is 0 volt. Now amplitude is reduced, made half or 1/4 or something like that. So it will go up to this point. It will come here. It will go up to this point. It will come here. It will go up to this point. It will come here till it touches 0. And after that, it will be the same half magnitude. So here to here it was 2V. Here to here it will be your V. Because amplitude has become half. So it grows like that. Could I make the point clear? What way conceptually the signal will be growing in the steady state, growing in the transient state to reach the steady state value. When the magnitude has reduced, it has touched over there. Once again, the magnitude increased. It will not go beyond this 0. It will remain like that only. Once it has touched 0, it will keep on coming like that. Even if we increase the magnitude also, but if magnitude reduced, it will start growing exponentially to that place. Okay? Any question? Coming to your mind? No. Fine. So these 3 tips I have given you to solve complicated numerical problems also. Remember, voltage across the capacitor is drop across all the resistances in series getting subtracted from the input. That is the voltage across the capacitor. And when it is steady state case, at that time only you can say what is going to be my minimum amplitude of the signal and what is going to be the maximum amplitude of the signal. Maximum will be 0, of course, until some reference is given, and minimum will be according to that. You have to compute. On a steady state, that is the minimum in that case, not in the transient response. I think transient response, they will say that after second time period, what is the minimum? That kind of question you can explain. But when it is asked as such, you are solving that in the steady state response. Coming to what else was I trying to say? Okay, those things I have done. Now I'm coming to this point. When I take that, see, always we draw source resistance closer to my source voltage. Okay, and here is my diode. This resistance you can put yourself, then that's not a problem. Here I am putting that resistance now. This is going to be my V naught. Okay, this is my VI. VIT will be given as some signal sinusoidal as square wave. If the calculation is expected, it will be given as a square wave with certain time period also. Because sine wave, we don't expect you to solve in 1 hour time, because amplitude will be changing very frequently and it will be having a sinusoidal shape. It is square wave, it's fine. If it is sine wave, then what will happen? Here will be your VIT into e to the power minus t by r dash c. R dash will be r parallel to something, and in series with this RS. RS also is coming into that picture. So VIT into this thing, okay, will be the signal that will be appearing to the capacitor, appearing to the diode. Here, that is the signal that will be appearing to the diode. If it is square wave, constant voltage into e to the power minus t by RC will be coming. Here, if it is sinusoidal one, write a sinusoidal signal, multiply by that. So that's what I'm saying. For calculation, sinusoidal signal may not be expected by the examiner to make solve the problems by computation or so. It is minus t by RC. For various t, it will be giving that kind of your attenuation over there. Here again, time period t by 2. So 0 to t by 2, it will be one kind of this thing, and t by 2 to t will be another kind of expression for the charge discharge in sinusoidal case. So this will be sine, but this discharge etc. will be charging will be taking place. Charging will not discharge. Charging will be taking place according to this duration, in which forward resistance and reverse bias resistance, reverse resistance of the diode will come into picture. Anyway, I'm talking of the square wave. Okay, I'm talking of the square wave. It should not be. Okay. Here is my square wave. I'm drawing. Is that gone? Here. Here is my V mean. It can have any value. You can put it over there. Negative, it will become minus like that. This is your V max. Okay, and the square wave, symmetric square wave. Okay, I think instead of complicating the situation, we are going like that. Here is my 0 reference. Okay, so this one we are applying to this circuit. Okay, I want to find what is the clamping voltage VCL, that is V naught at clamping. It will be V naught maximum, you can say. After at clamping, what is V naught maximum? Because DC we are not clamping, clamping the maximum value to 0. That's what. So V naught at clamping will be given by this voltage VCL. So will this clamping make it 0 or it will remain above that? We have to see that. VCL, V naught at clamping, because diode is there, I am going to take diode characteristic into consideration. Read it carefully because in basic electronics you have read it. Okay, so doubt is there, you can ask. Diode characteristic considered. Okay, diode characteristic is considered. It is coming like this. So what happens at the VCL? What is going to be my current through the capacitor, or you can say current through the diode, ICL. is current through diode. A diode current I can write here. Diode current at clamp voltage. Okay, that maximum voltage or so. So this ICL will be given by reverse saturation current. You remember this thing? E to the power across the diode voltage is VCL. Even if R is there, remember this R is there. So even then across the diode voltage is VCL. So this VCL divided by this eta and this VT. You know this barrier potential is VT. Okay, barrier potential of the diode, that is manufacturing data dependent thing. So and eta is your charge, electronic charge divided by Boltzmann constant into absolute temperature. Okay, so that way it comes like this. So VCL, no, sorry, it is the other way around. VT itself is going like eta is 1, 2, or 3, something like that is coming. Okay, fine. I think you know better about that. I have written the value here. Okay. So this is my this thing. Diode current is this. So how much is the capacitor charging current? Capacitor charging takes place. This R I have considered here. Okay, I'm putting here once again. Capacitor charging current will be ICL plus current through this resistance R, that is your VCL by R. This can be neglected. For the time being, I'm neglecting. If you are asked to do like that, you have to consider that VCL by R also in the charging current also. I'm taking only ICL for the time being for the sake of explanation. VCL divided by R is another current. Both currents are passing through the capacitor. RS current and C current is the same. Okay. Now diode characteristic have taken into consideration. What is going to happen now? Let me see in the next page. Yeah, here. So what I have seen, capacitor charge current is CL and that must be equal to discharge current in steady state, because charge inside the capacitor should be either 0 or should be some constant value. So this is your capacitor discharge current. So ICL you have seen is your I naught e to the power VCL by eta VT denominator. I'm not putting the bracket here. You understand what I'm going to say. What is the discharge current? Diode becomes reverse bias. So your R parallel to RR is the resistance plus RS. Through this capacitor will be discharging. Okay? RS is very small, RR is very large. So you can say this one will be your V max minus V min. I'm talking of discharge, okay? By R. Why I'm writing here? Anybody? Who does not agree to that? Let me put here. What is going to be my VC max? Across the capacitor, the maximum voltage will be V max minus VCL. Across the source resistance, I am considering as 0. Across RS, the drop I am taking as negligible. So it V max minus VCL is your VC max across the capacitor maximum voltage. What is my VC min? VC max minus, when the V min is appearing, it will be dropping by that. So it is your V min, not VC min. Okay? So VC min is your VC max, and what is VC max? It is your V max minus V min minus VCL that is equal to V minus VCL. V was the difference of the V minus VCL coming over there. So this is the difference is your V, and that difference divided by R. Okay, V max VC minus VCL divided by R is the discharge current. The discharge current, I discharge. Steady state, both of them are equal. So if you solve it, this becomes your V minus VCR. I'm writing here. V minus VCL, it is VCL, not R. VCL divided by R. I will solve it. What is my VCL? E to the power something is coming, remember? ICL was how much? ICL was I naught e to the power VCL divided by eta Vt. So I solve it. So VCL will become equal to eta Vt eta Vt ln natural logarithm V by R I naught. See, the resistance R has come into picture. For the discharge, V by R is coming. So this is the condition I have got. So if I consider the diode Cartesian into account, my VCL clamping voltage will be dependent on this V. V is large, VCL will be larger. V is small, VCL will be smaller in magnitude, because V is positive always. If V max has become negative and V min is also negative, then in that case it will be, the V will be once again difference of the two, max minus min will be positive only. So that's what the VCL will be according to that. So if V is increasing, difference between the voltage is increasing, VCL is increasing. What is my dVCL? dVCL by dV, let us say. I do like that. He needs a VT. I think you know how to differentiate. I need not expand the I naught divided by V. So what happens? The change in VCL clamping voltage with respect to increase or decrease in your voltage difference of the square wave will be smaller. This change will be smaller if V is larger. If V is larger, VCL is larger, but the change, relative change there with respect to that V will be smaller if V is larger. This is the beauty of the diode characteristic consideration in your this circuit analysis. Okay, and that's why we try to increase this V. So the circuit in the practical case we make is, this is my R, this is my C, this is my R, the RS, this is my R. Here I give a voltage and here is my diode. Okay, in this case your V will be increased by this voltage. Suppose this I am putting as your VYY, DC voltage, VYI. So VYI will get added to this V. Okay, and current will be accordingly changing because VYI and V will get added, divided by R will come into picture. So current also according to that we can compute like so voltage V across the diode, voltage V appearing over here. Okay, that was coming as a some kind of filter output also from the capacitor. So that one added with VYY appears here, and that's why VCL I can control to whatever level I want by making this VYY larger. And if I am increasing VYY, at that clamping voltage, the fluctuation will be very, very small. Larger the VCL clamping voltage, smaller is the fluctuation by considering diode characteristic into account. Is it okay? This completes everything. Anybody who didn't agree? Or you have to solve it yourself, otherwise you cannot get it. There is another one, synchronize clamping. That is simple one that you can write in a better way than me. It is like this. Okay, here is my R. Here is my diode. This diode I put it to a switch. This switch is S. Diode is forward bias, reverse bias as usual, the way it is coming. Now I am putting a switch. So when the switch is open, it is working like a high pass filter. I am getting the output. When the switch is closed, it works as a clamper. Okay, so this is becomes synchronous. This will be synchronized with the input given to the switch. Synchronous. Synchronous clamper. Okay, so synchronous clamper is such that here I will be giving some kind of pulse train to control the switch. Whenever this pulse is on, it works as a clamper. When the pulse is zero, that means switch is off, it works like a filter, where only DC blocking is taking place, no clamping is taking place, DC blocking is taking place. If it is opened for longer time, so that steady state it is, DC blocking takes place. So when switch is put, you will be asked to reply the answers under steady state condition only. When the switch is closed, it works like a clamper. Once again, you evaluate this in the steady state case only. The synchronous will not be expected as a question in transient state. Only steady state, both the cases will be considering. Switch is on for longer time, switch will be off for longer time. Okay, so that's what is this thing. And for practical cases, your time constant RC, if I'm using this R here, RC should be as large as possible, much larger than 1. Capacitor should be large, R should be large. Then it is a practical one. This kind of discharge will not take place. If R is, it has become like that. If C is very large, this tip will be almost flat. So C is very large and R is very large because discharge also should not take place here. Or because the negative charge should not take place. So it will be almost constant here. It will coming like that. Okay? Clamping, I know, if it is clamped here, it should come like that. So the 0 has gone, 0 has come over here. It becomes flat, it becomes flat. So R and C both should be very large. Source resistance may be small. Your forward RF might be small. RR can be large, fine. But R and C should be large. That is the practical clamper circuits. And the second thing, if are including this one, diode characteristic in your design, you should have one reference voltage V added, VYI added here. So your fluctuation in the clamped voltage will be small and level at which is clamped, that will be large. I have completed now this module 2 and the tutorial that I wanted to talk. Any question? I welcome. Okay, friends, no question. So I wish you good luck for your module 2 test on module 2 exam, rather I can say module 2 exam in your this thing. Many students are not there today. I don't know what to do because here I have got some kind of thing that attendance has to be anyway. I'm not taking, other teachers might be taking your attendance. They will be passing that to the academic section here. So you should be careful that way. You are creating problem for yourself because if any other teacher report, it will be in trouble. I am not getting that data, so it's my duty only to warn you, give you some kind of your alarm that way. Okay. So Sengupta, should we discuss today now?
Yes, sir.
Okay. So good day. See you on Monday in the class, class test. I think they have given notice to all of them because many are not there. Absent means mark them 0. I think they know, consideration for them. Exam somebody is missing, 0, simple 0. That's all. You will pass after 4 modules only.
Yes,
okay?
yes.
So that is the re-examination, the module, I think I will disagree to that. Anyway, let us see. There is no valid reason. There cannot be so many valid reasons for many people. Okay, it's fine then. Huh?
Okay, sir.
Okay.